Okay, so in the previous video, part one of this section, we evaluated a few limits. In the last couple of examples we went through, even though we made kind of a long argument with our work, kind of using the limit laws, we saw that the end result could have been attained by just using direct substitution. So we could have done it much faster just by plugging the number in that x is approaching. That is usually not going to work because most of the limits that we are going to be evaluating in this class, the ones that show up in applications and things like that, direct substitution is going to not work because the number that we would be plugging in won't even be in the domain of the function. So to show you what I mean, this limit right here that we're going to evaluate, it's the limit as x approaches 5 of this rational expression. But if you were to plug 5 in to the x's here, if you were to use direct substitution, this thing reduces down to 0 divided by 0, and you can't divide by 0. So does that mean that the limit doesn't exist? Well, no, the limit absolutely exists, but direct substitution will not get us there. So what we're going to use is this little theorem up here. It says if f of x and g of x are equal, whenever x is not equal to some number a, then the limit as x approaches a of f of x will be equal to the limit as x approaches a of g of x, provided both limits exist. Now, what this means is that we're looking at two functions that are identical with the possible exception of one point. And here's where this applies in this example. I'm off to the side here. I'm going to take that rational expression, x squared minus 7x plus 10 over x squared minus 25. I'm going to simplify this rational expression. So I can factor my numerator here. It's equal to x minus 5 times x minus 2 divided by, I'm going to factor my denominator too, x minus 5, x plus 5. Okay, now from algebra, you would know that we could cancel these two factors right here, these x minus 5s, which gives me x minus 2 over x plus 5. However, even though you're probably used to just canceling that x minus 5 out from your numerator and denominator and writing this function is technically not exactly the same as this one, even though this is just the simplified version of this. And the reason I say that is because in this expression, if you plugged a 5 in, you would get something that's undefined. Whereas in this expression, if you plugged a 5 in, you would get something that is defined, 3/10. So if these two things are supposed to be exactly equal, then they should give us the same number no matter what I plug in for x. But plugging in 5 is the one place where these two expressions will differ. So you don't normally add this, but if you want these two expressions to be the same, you have to add this condition of this is equal to this as long as x is not equal to 5. But we are plugging 5, or we are taking a limit as x approaches 5. And so here's basically what this means for us. Let's suppose that here I have the graph of f of x, and let's suppose f of x has a hole in its graph right there. And let's suppose g of x looks identical to f of x, except there's no hole. G of x. Okay, so there's a point there as opposed to a hole there. Just scooch that down a little bit. Even though this function is not defined there, whereas this one is, the limits of both functions as x approaches a is going to be the same number. I can see that we're at least approaching the same thing in both cases, because it doesn't matter if this function's not defined at a, we can still find its limit as x approaches a. And so what happens in a case like this, if we're evaluating this limit, we see that direct substitution does not work as written. But after simplifying that rational expression, I get something where direct substitution would work because my limit laws allow me to take that limit and bring it up into my numerator and my denominator. And then if I were to go through all the work like I did in the previous video, I could see that my result would come out to the same thing that I would get from just plugging 5 directly into this. So over here, I'm going to do my work. The limit as x approaches 5 of this rational expression, according to that theorem, will be equal to the limit as x approaches 5 of this simpler rational expression, x minus 2 over x plus 5. And for that, I would just plug 5 in directly. 5 minus 2 is 3. 5 plus 5 is 10, 3/10. Okay? Now, if you wanted to, you could go verify that graphically. You could plug in this function into a graphing calculator. I recommend using Desmos if you haven't used that before. It's a free graphing calculator online. Just search Desmos. It's a fantastic utility. And you can see graphically that this is what we should be getting, 0.3 or 3/10. Let's try that again with another example. So here I'm evaluating the limit as x approaches 9 of another function that involves a quotient. So 9 minus x over 3 minus square root of x. Now in a case like this, you would first think about whether or not your limit laws apply. And because it's a quotient, we're tempted to use, let me go back to that page, we're tempted to use limit law number 5, which says I could bring my limit into my numerator and denominator separately. But this is subject to the condition that the limit of my denominator as x approaches a, or 9 in our case, is not equal to 0. That is not the case for this function, because my limit laws, if I were just taking the limit as x approaches 9 of 3 minus root x, my limit laws would allow me to use direct substitution here, and 3 minus the square root of 9 is 0. So I can't just plug things in directly. Instead, I'm going to do this. Let me rewrite my limit here. Limit as x approaches 9 of 9 minus x over 3 minus the square root of x. We're going to attempt to simplify this expression. And we're going to use a trick that's really, really useful in evaluating limits like this one, multiplying by a conjugate. So if you don't remember from algebra, when we have an expression like 3 minus the square root of something, or a number minus the square root of something, for example, the conjugate of this expression would be 3 plus the square root of x. And I'm going to multiply by 3 plus the square root of x over 3 plus the square root of x. This is a valid thing to do because this expression is the same thing as 1. I'm multiplying this by 1, and we know that multiplying a number by 1 does not change it. So I haven't altered anything by doing this. But now I want to do that multiplication. So let's see what that would work out to. I would multiply through, so 9 times 3, that's 27. 3 times negative x will be minus 3x. 9 times root x, that's plus 9 root x. And I can already see that I made a critical error here. I'm glad I did because I want to point something out. When you're doing these long limit problems, it's very easy to forget to write that limit every step of the way. So I'm going to redo that step because I had already forgotten that. Limit as x approaches 9 of 27 minus 3x plus 9 root x minus x root x. That's what my numerator would multiply out to. Down here, we think of that as like a difference of squares. So I'm multiplying this expression by this one, and I'm going to get 9 minus x out of that. That's going to be my end result. Okay, now let's see if we can simplify things even further. So I have the limit as x approaches 9. I don't really have any common terms here, but I do think I could probably do some factoring by grouping. So for example, if I were to group up these terms here and these terms here, I could factor a 3 out of these two terms, which would give me 3 times 9 minus x. I could also factor a root x out of each of these terms. So that's going to give me plus root x times 9 minus x there over 9 minus x. And then I could factor a 9 minus x from each of these. So this is going to give me the limit as x approaches 9 of 3 plus root x times 9 minus x over 9 minus x. And notice, just like in the previous problem, we get things that cancel out. So this becomes the limit as x approaches 9 of 3 plus root x. Okay? Now, I've taken this function and I've simplified it to a much simpler function, a much simpler looking expression. And this function and this original function up here are equal to each other, with the one exception that this one is not defined when x is equal to 9, but this one is. So according to that theorem up above, I could just evaluate this limit instead of working directly with the original limit. And this is one where we could use direct substitution using those limit laws. So this would be equal to 3 plus the 9 is going to be plugged in for the x, which is 3 plus 3, or 6. Okay? So that is a general strategy that you're going to see used a whole lot throughout this chapter where you're evaluating limits. If the limit is not something that you can use direct substitution on right away, you may need to simplify the expression that you see there until direct substitution does become an option. Let's take a look at another one. This is a function and a difference quotient that we've encountered already. This, I think it was section 2.1 actually, where we introduced the velocity problem. So here it says let s of t equal 4.9 t squared, and we want to evaluate the limit as h approaches 0 of s of 5 plus h minus s of 5, all divided by h. Back in section 2.1, I believe, we looked at this function. We said this is the function for free fall. What it does is it gives you the distance in meters that an object has fallen t seconds after it's been released. Okay? And we actually evaluated this limit back there, but we did it numerically. I believe we got 49 as our answer. We created a table of values, and we showed that as h came closer and closer to 0, the difference quotient was giving us values that were closer and closer to 49. But now we don't have to use a table. We're going to confirm that result by evaluating this analytically or algebraically. So first of all, the limit as h approaches 0 of this expression, can I use direct substitution right away? Well, if I did, this would become s of 5 minus s of 5, which is 0, over 0. No, 0 over 0. I can't calculate that because I'm dividing by 0. But again, that does not mean that the limit does not exist. It just means I have to approach it differently. So what I'm going to do is plug or use the function as it's been defined and see what I can do to simplify things. So we're looking at the limit as h approaches 0, and s of 5 plus h would look like 4.9 times 5 plus h squared minus s of 5. This is equal to 4.9 times 5 squared, all over h. Okay? Now, I'm going to start expanding things and combining like terms and trying to simplify things as much as possible. But the first thing I want to pay attention to is that this 4.9 here can be factored out of my numerator, and according to limit law number 3, I can bring that constant, that 4.9, clear out of the limit entirely. So I'm going to do that first. This is equal to 4.9 times the limit as h approaches 0. And now the 5 plus h squared, I'm going to expand that out. That's equal to 25 plus 10h plus h squared. And then here, minus, remember we pulled the 4.9 out, 5 squared is 25. All over h. And now I'm going to simplify a few things all in one go. So first of all, 25 minus 25, we get cancellation there. And then if you notice, every term that's remaining has at least one h in it. So that's what's going to allow me to cancel some h's out. This h will cancel with this h and one of those h's. Notice how much I just crossed out. What's really left here? 10 plus h. So this is equal to 4.9 times the limit as h approaches 0 of 10 plus h. Now at this point, we have a linear expression here. And as we've already seen, our limit laws allow us to simply plug 0 in for this h, because I no longer have any divide by 0 errors occurring anywhere. So this becomes 4.9 times 10 plus 0, which is just 10. And of course, 4.9 times 10 is 49. The exact same result we got before, but now there's no guesswork involved. We're not looking at a table and saying, it looks like the limit is 49. Now we know with certainty that it's 49. Okay? So this technique is more useful than what we have done so far. Let's take a look at another example. And now the function that we want to take a limit of is a piecewise function. So it's given here. And we're asked to determine if the limit as x approaches 1 of f of x, where this is f of x, where f of x is this function, whether we want to show whether it exists or not. Let me restate that. We want to determine what it's equal to if it does exist, or we want to show that it doesn't exist. Now, if you look at the graph that I gave for this function down here, you can see that at 1, which would be right here, the curve has a break in it. Okay, so we talked about left and right hand limits before. In this case, the left hand limit of this function appears to be approaching 2 as x approaches 1 from the left. As x approaches 1 from the right, we appear to be approaching some number around here. Looks like that would also be 1. We're going to confirm that by working with the piecewise function. So rather than try to evaluate this limit all at once, I'm going to look at left and right hand limits. What is the left hand limit as x approaches 1? Remember, that's what the little minus sign represents there. Okay, well, that would be equal to the left-hand limit as x approaches 1. Now, remember, what we're doing when we take a limit from the left is we're using values of x that are slightly smaller than 1 to evaluate our function, or to approximate our limit. And I'm looking at this, I'm realizing there's a typo here, so this should be greater than. Otherwise, our function doesn't really make any sense. So a piecewise function, the inequalities over to the right tell you when it's okay to use the function appearing to the left. And when we're using values of x that are smaller than 1, that falls under this part of my piecewise function. So as long as x is less than 1, f of x is defined by the expression 3 minus x squared. Okay, now whether we're dealing with a left-hand limit or right-hand limit or a normal two-sided limit, this expression being quadratic, being a polynomial, we can evaluate this by direct substitution. So I'm going to plug a 1 directly into this. And don't confuse this for a negative 1. It's not negative 1. The minus is not appearing in the right place. It's just 1. This would be equal to 3 minus 1 squared, which is equal to 2. Okay, now let's evaluate the right-hand limit. What is the limit as x approaches 1 from the right? Well, remember what that means is I'm approaching 1, but only by using values of x that are greater than 1. And after fixing my typo here, we can see that the part of the piecewise function that would apply in this case is this one right here. So I need to use this expression instead of the one on top. I almost did it again. Limit as x approaches 1. It's very easy to forget to write that limit. Limit as x approaches 1 from the right of the square root of x over the natural log of x plus 1. And again, we would apply our limit laws here. can I bring the limit into my numerator and denominator? Remember, the only real issue with that is if the denominator has a limit that comes out to 0. But that's not the case here, because if I brought this limit into my denominator, then I'm looking at the limit as x approaches 1 of the function natural log of x plus 1. I can use direct substitution there because the natural log of 1 is 0. So this becomes 0 plus 1, which is 1. And doing the same thing in my numerator, putting a 1 in here gives me the square root of 1, which is also 1. I get a 1. And remember, we sort of said that's what we were expecting to happen based on this graph. So as you can see, my left-hand limit gives me one value, my right-hand limit gives me a different value. And as we said before, if a two-sided limit is going to exist, then the left and right-hand limits both have to exist and agree with each other. So I would say something like this. The limit as x approaches 1 of f of x does not exist because the limit as x approaches 1 from the left of f of x is not equal to the limit as x approaches the 1 from the right of f of x. Okay, that's all that needs to be stated there. I'm going to go ahead and stop this video, and we'll keep going in part 3.